Okay, this is section 7.5. If you've got a book, we're on page 397. I'm turning that page pretty quick. Just wanted you to see the title to this is Properties of Trapezoids and Kites. And here's what you gotta do, folks. You gotta think, okay, I've learned everything I can about all time kinds of parallelograms. Parallelograms in general, and then specific ones like rectangles, squares, and rhombuses. We are no longer talking about parallelograms. This section is about quadrilaterals with certain properties. They are not parallelogram, okay? Trapezoids and kites are what we're going to talk about. And you turn the page where the section begins. We're going to talk about trapezoids first. There's a little bit of notation, vocabulary, if you will, whatever, the way we write things. First of all, a trapezoid is a quadrilateral. That's what this whole chapter is about. It's a quadrilateral. It's not a parallelogram. And a trapezoid is a four-sided figure where exactly one, not both, not even a chance that both could be, otherwise it'd be a parallelogram, where exactly one pair of sides, opposite sides, are parallel. The other ones are not in a trapezoid. Now, generally we draw trapezoids this way, but I need you to know that they could be drawn like this. And these would be the parallel sides. They would be vertical this time. In either case, whether they are a top and the bottom or a left and a right, the parallel sides, in either case, we call the both of those sides bases. I'm going to call this one, the book doesn't do this, but I'm going to, and it helps clarify things a little bit. I'm going to call this one big B. I'm going to call this one little b. Because if you think about it, if you have a trapezoid, you will always have one of the parallel sides longer than the other, because if they were the same length, you'd have a parallelogram, right? We do not have a parallelogram. We talk about trapezoids. So there will always be one that's longer than the other, and I will refer to the longer one as big B and the shorter one as little b. And that's a little bit ambiguous because usually we reserve capital letters for points, but if that is clearly not near a point, I'm going to call that big B for the longer base. So in this case, this would be big B here, and this would be little b here. Base does not mean bottom. Base means parallel to the other side. Okay, so these are the bases. There's two bases. And then there's these guys over here, these guys that are not bases, that are not parallel to each other, we just call those legs. So the legs can't be parallel, because if they were, you'd have a parallelogram, which we do not. These are trapezoids. Now, if you happen to have a trapezoid so that the legs are the same length, then you have an isosceles trapezoid. And the reason why we call it an isosceles trapezoid is because really, if you think about this thing that I've got, it was really, and I don't know if I'm tall enough to get this all out here, but it really was, what we had was an isosceles triangle that had its top whacked off, right? If you whack that off in such a way the slice is parallel to the base of that triangle, you get what's called an isosceles trapezoid, and you're still left with these two pieces being the same length because they were cut off parallel. In that case, oh, by the way, let me come back over here. This angle right here and this angle right here, they're called base angles. This angle right here and this angle right here, they are also base angles. But in an isosceles trap, both pairs of base angles are the same size because they come from an isosceles triangle where the base angles are the same. See if I can convince you of that. If this was actually a trapezoid that was created by lopping off the top of an isosceles triangle, then if it was an isosceles triangle first, we know for sure that this angle was equal to this because that's what isosceles triangles have. If we chop it off with a line parallel to this one, then this angle and this angle that we lost are the same because they're corresponding between parallel lines. These are parallel, which means it leaves the same amount for those two when you lop it off, when you cut it off. And so these base angles are the same. Base does not mean bottom. It means the angles made with the bases and the legs. These two angles are the same, these two angles are the same, and these two angles are supplementary. So if you know one angle in an isosceles trapezoid, you should be able to find the others. You okay with that? Yep. All right. There's another property of, let's see. Let me see if I can write these things down. The definition of this, the definition of a trapezoid, any trapezoid is if a quadrilateral has exactly one pair of parallel opposite sides, then it's a trapezoid. I should have written that down first, so I had to kind of cram it in here. But it's an if-then statement. If a quadrilateral has exactly one pair of parallel opposite sides, it's a trapezoid. If it's a trapezoid, then it has exactly one pair of parallel opposite sides. So this reads backwards and forwards, this if-then statement, because it's a definition. Definitions are biconditional. Okay. We talked about bases and legs and where they are, and that bases don't have to be top and bottom. They could be right and left. Come back over here to the idea of isosceles trapezoid, where we kind of straighten the thing up, where we make these base angles the same, these base angles the same, these legs the same. You got an isosceles trap, and these are properties of an isosceles trapezoid. Definition, that's a property of this, but this has a few additional ones, like isosceles traps imply two, well, you don't have to write two, imply equal base angle pairs. That's this right here, saying this equals this and this equals this. That's a property. Here's something else that might not have occurred to you, but it's true. Isosceles trapezoids have or imply equal diagonals. Now, let me show you this over here then in a trapezoid that's not isosceles. I could use either one of these, but this has already got a lot of marks in it. You can see that if I drew this diagonal, that's going to be a lot longer than this diagonal. So they are not the same. It's pretty clear, right? But if you draw the diagonals in this guy right here, where it's been straightened up and the legs have been made to be the same length, then this diagonal is as long as this one. And I'm not going to write it as a property, but this triangle that's on this side over here is going to be equal to this triangle. Obviously, these two are not equal. This one's way bigger than this one, but these two guys on the side there that are made up of the legs, where part of a triangle has part of the legs as part of them, they're going to be equal triangles. And the sides of those things right there are going to be equal. The diagonals are also going to be equal. So that's properties of isosceles trap. So with that in mind, learning those couple of things, let's see if we can figure out. Example 1 takes a long time. So please stay with me on example 1. What we have there is a trapezoid. It looks like a trapezoid anyway. We've got 4 points that have been connected to make a quadrilateral. We've got 0, 0, 0, 3, 2, 4, and 4, 2. It's connected like that. And I'm going to change the direction on this just a little bit so that these people can see it over here on the grid. I don't know if you can. I hope so. Okay. What we're trying to do is decide if this is a trapezoid, and if it is, if it's isosceles. How do you decide if something's a trapezoid? It's kind of difficult, and it seems kind of tedious and silly, but because it's clearly this side is not parallel to this one, right?
Yeah.
But you have to establish that. See, in order to prove that something is a trapezoid, not isosceles or anything like that, just a trapezoid, you have to prove that two sides that are opposite of each other are parallel, and also that the other two are not. You can't just prove the sides parallel to be parallel. The other might be, obviously they're not, but if you're going to do an actual proof here, you're going to have to write it all down. So if I have that thing right there, I'm going to put the letters on so I can refer to them. O-R-S-T. So what I want to do, was fairly obvious from this picture, is prove that RS is parallel to OT, right?
Yes.
We do that with slopes. So we say the slope of RS equals, and we count it. RS, if I start down here low, I'm going to have to count up 1 and run 2. So the slope of RS is 1, rise over run, 1 over 2. And I want to find the slope of OT and see if it's the same. It is. We know it is, but we're gonna count it. If I start down here at OT, I'm going to have to rise up 2. Then I get to run 4. So I have the slope of that is rise 2, run 4, which is 1/2. Therefore, RS is parallel to OT. So that's one thing we have to establish. You okay with that?
Yep.
Now what we got to do is find the slope of RO and ST and show that they are not the same. So I'm going to say the slope of RO, and this has to come from your algebra experience. The slope of RO cannot be counted. What it is you would rise 3 and run nothing. 3 over 0 is undefined. And we really shouldn't even use the word or an equal sign. The slope of RO is undefined. You need to use the word is because it's not equal to an undefined. Undefined is, we don't know what that is. It's not defined. I want to find the slope of ST. And it is rise 2, run backwards 2. So it is 2 over -2, which is -1. This implies that RO is not, that's how you write not, just like not equals is like that, is not parallel to ST. Therefore, ORST is a trapezoid by definition. This is your evidence. You have two sides that are opposite that are parallel. You have two sides that are opposite that are not. Therefore, that thing is a trapezoid. Now, question is it isosceles? How do we figure out if something's isosceles? We got to find the lengths of the legs. Because we have no way on this grid to figure out angle sizes. If I could, I might try to prove that this angle was equal to this one, and this one was equal to this one. But angles are really tough to come up with unless you're taking trigonometry, of course. So we're not going to come up with angles on here. Instead, we're going to go by definition of isosceles, and we're going to try to prove that this length is equal to this one. So we test that out. I'm going to come over here. I don't know if you guys that are watching this can see this, but hang on. We're going to be at a slight angle here. I'm going to go over here. Uh-huh.
Are we going to have a lot of these on the assignment?
Nope. Oh, okay. So now what I have to do is try to figure out if RO is equal to ST. So I say the distance from R to O, and I can just say that's 3 because I counted it. Because it's a vertical thing, you can just count it.
Yep.
I'm going to find the distance from S to T. That I'm going to need the distance formula for. And this is how you do it. I'm going to put the coordinates for S on here. That's 2, 4, and 4, 2. And if you remember the distance formula, it says subtract your x's. 2 minus -4. Sorry, it's not -4. 2 minus 4 is -2, right?
Yes.
You can do that in your head, and you can also square it. 2 minus 4 is -2. -2 squared is 4. Write that right there. You don't have to show me all the work that goes with it. We do that to the y's. 4 minus 2 is 2. Squared is 4. And so this is equal to the square root of 8, which is equal to 2 root 2. So RO is not equal to ST. Therefore, ORST is not isosceles. So here we established that it was a trapezoid. Over there, we took a look at the lengths of the legs. They were not the same, so it is not an isosceles trapezoid. It is merely a trapezoid. Follow that? That's what's going to happen grid-wise. Most of the exercises you do are not on a grid. Let's take a look at your exercises for a minute. Let's see how many times they put things on a grid. On page 403, take a look. It looks like numbers 3 and 5, those are assigned. Numbers 3 and 5 are going to be gridded. Yeah? Because they got points. You have to put them on a piece of graph paper and see what's going on. After that, when we get to number 7, you see all the drawings. Oh, you get to number 13. It looks like more grid work there. There's 3. We got to do 13 is assigned. Then, I don't see any other places where you have to plot points or any other grids on the exercise. So it looks like maybe 3 of those types you might have to entertain. Okay? Okay, so let's go back. So that was example 1. Okay. So I want you to look at the top of page 399. And it gives you those theorems that I've already given you. It's just in a formal way in the book. It says the isosceles trapezoid base angle theorem. That's that one that says if it's isosceles, both pairs of base angles are equal. Theorem 7.17 is the base angle's converse. Now that one I didn't write down because both of these said isosceles traps imply. So it means if you know it's isosceles trap, you can be sure this is true. But it's also true, this one also has a converse, and it says if both pairs of base angles, boy, this is a long one, in a trapezoid are equal. Boy, that's a lot of stuff before the implies. That implies an isosceles trapezoid. So if you've got a trapezoid, you know it's a trapezoid, and you can establish for some reason or another that both pairs of base angles are equal, then you can say it's an isosceles trap. Actually, if I remember right, I'm pretty sure I do. You can just write if the base angles, and it can be either pair or both. If the base angles, either pair. Because if this is equal to this and it's a trapezoid, these have to be because they're supplements of those ones that were equal, right? So one pair is enough. You don't have to have both pairs. So if the base angle, either pair in a trapezoid are equal, then you know it's an isosceles trap. So that's the converse of this. That's the second statement at the top of page 399. And the third one is the one about the diagonals. If you have an isosceles trap, then when you draw the diagonals, you can be certain they are the same length as well. They do not bisect each other. The diagonals do not bisect each other, because if they did, you'd have a parallelogram, right?
Yep.
Yeah, so they don't bisect each other, but they are the same length. Take a look at example 2. It's got a strange picture of something real there. I don't know what it is. It looks like it's part of I don't know what it's called. It says, the stone above the arch in the diagram is an isosceles trapezoid. Find the measure of K, M, and J. You see that they tell you L is 85? Then how big is K? 85. How big is J?
95? No, wait.
You can grab your calculator if you want, or verify it. What do you think? J is 95, yeah, and M is
95.
95. So if you can do the subtraction either with the calculator on your paper and get it right, then you seem to know what you're doing. It's just that you're worried about the arithmetic. So I'm not too concerned about you doing one like that. Here's something else cool about trapezoids before we move on. I'm going to erase this so that we can stay on this board. Sorry about that if you're watching. I know it makes you dizzy. Okay. About trapezoids in general, not just isosceles. It's true of them as well, but has to do with a thing called a mid-segment.
Jazz band, go to the band room. Jazz band, you're excused to go to the band room.
Okay, so let's just take any old generic trapezoid like this. Is anybody in jazz band? Okay. Just take a plain old trapezoid like this, and I tell you this is parallel to this. A mid-segment means find the point that's in the middle of this leg, the midpoint. Find the midpoint of this leg and connect them. You now have a thing called a mid-segment. So if I have A, B, C, D for the trapezoid, and I have M and N at the end of this thing, then here's what's the fact about this one. The length of MN is equal to BC plus AD over 2. In other words, the mid-segment, mid means middle, middle means average. The mid-segment is the average of the two bases. That's what this is. If you write it in my kind of lingo, MN would equal big B plus little b divided by 2, because there's always a big and a small base. So this would be little b here, the length of it, this would be big B here. I realize there's a big B there too, but that one refers to that point, so it is slightly ambiguous, but this refers to the length of the base. If you average the bases, you get the mid-segment. Mid means middle, middle means average. Okay, so if you're aware of that then, which isn't too bad of you. Oh, by the way, there's one other property, and I think this is fairly obvious too, I hope. But if the mid-segment is right smack in between the two parallel sides, it's also parallel to them. So you get two things for this. You get that the mid-segment is parallel to the bases, and the mid-segment is the average length of the bases. Okay? So take a look at example 3. And I want you to see if you can tell me why Do you believe that MN is a mid-segment? On example 3. What causes you to believe that MN is a mid-segment besides the fact that it looks like it's in the middle? The marks on the legs indicate they've been cut in half, right? That's the key. So when we say a mid-segment, we mean the midpoint of a leg, which means that's equal to that, and a midpoint of this leg means this is equal to this. That right there is the evidence that this is a mid-segment, just so you know. Okay, so if that's true, then how long is NN?
How long?
How long is MN?
20.
20. How do you know? 28 and 12 is 40. 5 by 2 is 20.
Okay.
Did? Okay, moving on. Look at example 4. We're back to the grid again. It says use a mid-segment in the coordinate, or using a mid-segment in the coordinate plane. Find the length of the mid-segment ZY in trapezoid STUV. So if you've got a book, if you're watching this video and you've got a book in front of you, look at example 4. What we have to do is use the distance formula to find the length of SV. And we got to find the length of TU using the distance formula. And then average it. That make good sense? Okay, now watch how we do this without actually putting the thing on the grid. I'm going to find the length of SV. And the 2 points I'm using are 0.6 and 2.2. I'm only putting them up here so I can refer to them. 0.6 and 2.2. You wouldn't have to put these on your paper to do it. You can get it right out of the book. The distance between these 2 points is going to be, most of it happens in your head. It's 0 minus 2, which is negative 2 squared is 4. Am I going too fast?
No.
Anyone? 6 minus 2 is 4, squared is 16. So this length is the square root of 20. Now, if you remember from algebra, which I hope you do, this is better written 2 root 5. Anybody need a refresher on how you get that?
Maybe a quick one.
Pardon?
Maybe a quick one.
A quick one. This number right here, we have to see if there are any pairs of factors, things that multiply inside. So we prime factor it. 5 times 4. 5 is prime, so it doesn't come down any further. 4 is 2 times 2. Every time there's a pair of factors, it creates a perfect square. In other words, the square root of 4 is 2, but the square root of 5 doesn't come out of there. Every time there is a pair of factors, one of that pair gets to come out. Do you recall? Remember seeing this before?
Yeah.
So I prefer that you write it 2 or 5. Not only prefer it, if you write it like this on the test and you forget to simplify it, it's like forgetting to simplify a fraction. You will miss a point for not writing it in simplest form. So this one's length is 2 root 5. That's the short one that you see in the picture. The long one uses the points 8, 10, and 12, 2. 8, 10, and 12, 2. And I want to find the length of that one because that's the long base. 8 minus 12 is 4, squared is 16. 10 minus 2 is 8, squared is 64. 64 and 16 is 80. Now let's see what pairs are in 80. If I prime factor that, I'm going to get 8 times 10. 8 is 4 times 2. 4 is 2 times 2. Don't forget these guys that got left out. I sometimes, when I've got a whole string of things here, I sometimes bring that down at the end of its own stick just so that everything's on one row at the bottom. 10 is 2 times 5. So down here I have if I just bring them down, I have a 2 and a 5. Here's a 2. Here's a pair of 2s, and there's a 5 left over. And so this length right here is 2, which comes out, times 2, 4. Root 5 is the length of that one.
So it only works if there's 2 pairs of it?
No. If there's one pair, every time there's a pair of factors, one of them gets to come out. If more than one gets to come out, like here, a 2 gets to come out of that pair, a 2 gets to come out of that pair, whatever comes out multiplies together. This was not added, this was multiplied. Anything that doesn't pair up has to stay in. And if there was more things, like if there were a 5 and a 7 left over, I would put a 35 in here. They multiply together too. You with me? Okay, so this is better written 4 root 5. This one's 2 root 5. So now I have the lengths of those bases on this ugly grid there, and now I've got to average them. So I'm going to erase this stuff over here, which belonged to another problem. Hang on. So now I'm going to take 2 root 5, which is the short base, and I'm going to add the large base, 4 root 5, and I'm going to divide that by 2. Well, I'm here to remind you about radicals again. If you had 2x plus 4x, wouldn't that be 6x? Well, this is the same situation. You've got 2 of those root 5s plus 4 of those root 5s is 6 of those root 5s. And 2 goes into 6 3 times. That's the length of the midsegment. It's a lot of what we call radical arithmetic. Radicals because of these symbols here, not because it's radical. Because we're adding and manipulating radical symbols. Okay. So that would turn out to be 3 root 5. If you want to give me a decimal for that, you can, but he does not. The author of this book does not. He says the average is 3 root 5. Because it all worked out in the end. Any questions about that? It's a lot of stuff you have to remember from algebra 1. If you have trouble with those radicals, let me know. We'll work on it together until you get it back in your head. Now I want to talk to you about 2 more examples. I think, only 2 examples having to do with another quadrilateral that is not a parallelogram but has properties to it. It's called a kite because it looks like a kite, a paper kite that you put a tail on and 2 sticks that cross in the middle. And this is its definition, or its first property is this, that when you draw a kite, it will have 2 sides attached that are the same length. And the other 2 sides will also be attached to each other. They're adjacent to each other down here, but they will be a different length than those 2. So you've got 2 pairs of adjacent legs that are equal but different lengths from one another. Are you with me or not? That's a kite. It's a quadrilateral, 4-sided figure. 2 adjacent legs are one side, 2 adjacent legs are another, and there will be a shorter and a longer set. Because if they were all the same length, you'd have rungs, right? Mm-hmm. So you'll have a shorter set and a longer set of legs attached to each other, adjacent to one another. Okay, that's a kite. That's its definition. And these are some properties that it has. In every kite that you ever draw, and I'm not going to prove it to you. I could, but I'm not going to. If you take this diagonal and this diagonal, they will always be, in a kite, they will always be perpendicular to each other. That's a really nice thing. They'll always be perpendicular to each other. And one of the diagonals will be bisected. The other one will not. It's very clear. The one that's bisected is the one that connects the corners where one length meets the other. You do that diagonal that connects those corners where you've got a single mark and a double mark, where they meet. If you connect that corner to the other one that's like it, that's the one that's going to get bisected. The other one won't be, but they will be perpendicular to each other. So, one other thing. Right up here. The angle at the end of that bisected diagonal will be equal to the one at the other end of the whole quadrilateral. This entire angle right here will equal this one. This one will not equal this one. It can't. Otherwise, it would be a parallelogram. And it's not. Okay? So the ones at the end, and I don't want you to think about a short stick and a long stick, because believe it or not, you got some weird looking kites that you can get that are like this, where they could come way out like this. And this could be equal to this, and this could be equal to this. And so that when you connect the diagonals, this is actually the short stick. It is these that are equal, and it is this one that got cut in half. That's a little bit of extra stuff, but so it's not a long stick and a short stick. This is usually the way you see a kite. Nobody would try to fly this, but it's still a kite by definition, geometric definition. And so it's not a short stick and a long stick. Get over that. It's the diagonal, or the stick that comes through that joins the double mark to the triple mark. It's this one is like this one. It's that one that gets cut in half, and it's those angles at the end of that one that are equal. You can see very clearly that diagonal is not cut in half. So you got to get it straight where things are, because kites are not always a long stick and a short stick, where the short stick is the one cut in half. A lot of times it is, but not always. So take a look at example 5 with me, please. Example 5 actually has a picture of a kite to the left of it on page 401 at the bottom. Are you looking there? Mm-hmm. This kite's name is DEFG. And you can see that at E, we have a 115-degree angle, and at G, we have a 73-degree angle. What they want to know is, what's the size of angle D? Okay, so let me draw this, kind of like the one they've got up here, without all the colors and everything. See if we can figure this out. What do the angles of every quadrilateral add up to?
360.
I'm not gonna draw these. Sorry, how much do they add up to?
360.
360. This one was 115, I think, is what they told us.
Yes.
This one down here is
73.
73. These two, because they're at the end of, this is where we have the short sides joining the long sides. These two angles right here, we don't know what they are. But we do know they gotta be equal, according to that property I told you. Is that right?
Yep.
So if we take 360 and subtract 115 and 73 from it, and whatever's left, split it evenly, that should be the size of those. Does that make sense to you? Okay, and so you would grab your calculator. I'm gonna grab mine and finish this problem the way you probably would with your calculator. So we understand that all quadrilaterals, which these are, add up to 360, their angles do. So I would take the 360 total, and I would subtract 115, and then subtract 73. And what I have left is 172 for these two to share evenly. So I divide by 2, and I get that each of these is 86. See how we did it?
Mhm.
And so angle D is 76, or sorry, 86. You okay? Understand? Okay, one more thing, 2 more things. At the top of page 402, it summarizes everything you've learned this chapter, which is really, really nice. I would look at that, make sure you're convinced of all the things they're telling you before taking a test. At the top of page 402, in that gray stuff, they've got a big box at the top that's supposed to have all quadrilaterals in it. Any four-sided figure you can think of goes in that box. You see the one that leads off at the very far left of that big long box? You see it?
Mhm.
That is nothing particular. That is just a quadrilateral, and it doesn't belong, doesn't have any additional properties to it than it has 4 sides and 360 degrees. You know, there's nothing else about it. Now the next one's a parallelogram, so is the next one and the next one and the next one. And so they would all of those would filter down into the parallelogram box. See them? They're all there.
Yep.
And then if you get inside that parallelogram box and you say, okay, that first one.
Attention, please. Would you excuse the girls who are involved with distinguished young women? They need to be excused now. Thank you.
If you're in the parallelogram box, the one on the far left doesn't have anything particular except that its opposite sides are parallel. Well, and all the other properties parallelograms have. But the next one's standing up straight. And so we would filter him on down into the rectangle box. The next one is standing up straight. So that would filter down into the rectangle box. And the next one seems to have 4 equal sides, and that would come on down into the rhombus box. But so did the other one, that one that had 4 equal sides. So the square showed up in both of them. And if you drop that down into its own little toy box there, you get the square box, which is down there. It comes from both the rectangle and the rhombus. But all that stuff was learned before today. Then if you get back up there in that big old long quadrilateral box, then the one after the rhombus is a trapezoid. The next one's an isosceles trapezoid, and the next one's a kite. So a kite goes into a box of his own, and he doesn't have any other properties but kite properties. But the trapezoids both go down into the trapezoid box, and the isosceles one comes down with extra properties into the isosceles one. I like the organization of this. This kind of tells you how, and the farther down you go, the more specific and the more properties the thing has. Okay? All right. It doesn't tell you what the properties are. That's for you to know. And I'll give you a summary page before we actually test on this, but you cannot use it for a cheat sheet. You got to know the properties of certain things. Now look at example 6, and I'll show you how you're going to work this type out. Example 6 says, what is the most specific? In other words, what's the very, very bottom box you could put this diagram in? Now, it looks for all the world like a square, but there is no evidence that it is a square. It looks like a rhombus. If you look at it, there's no evidence that it is a rhombus. It looks like it could be a rectangle, but the evidence to be a rectangle would have to be the right angles in the corners, and there aren't any. The only thing we can tell from the markings is that the diagonals are bisected. That's a property of parallelogram. So based on the markings of this picture, even though it looks like it could be a square, based on the markings, the only thing you can conclude is that it's a parallelogram. because bisected diagonals imply parallelograms. There's nothing else that makes that diagram have right angles, equal sides, equal diagonals, nothing. There's nothing in there that indicates anything else other than parallelogram. So what it looks like is not definitive. It's what's marked and what you can conclude from it based on properties. You understand what I'm saying? This is only a parallelogram, that's all you can determine. Would you look at monitoring progress number 8? What can you determine about number 8? What? It is a kite. Can you tell it's a kite? Okay, because the RS and the UT are not the same length. So it is not a parallelogram. So it's gotta be one of the other two, either a trapezoid or a kite. It's gonna be anything. And it's a kite, because it has two sides which are connected that are equal, and the other two sides which are connected are equal. It's a kite. What do you suppose the next one is? Can you tell it's a trapezoid? You believe it's isosceles?
No.
No, because the diagonals are not the same length. What do you think the next one is?
Parallelogram.
What evidence do you have that it's a parallelogram? There's only one pair of opposite sides that are equal. We don't know about the other ones. There's nothing to indicate whether they're equal or not. We got a 9 there, but we don't know what the other one is. We also know that one of the diagonals is cut in half by the other, but we don't know that DF has been cut in half by the other diagonal. We don't know anything about that. Guess what you can conclude about that? Nothing. It is a quadrilateral. That's it. It's a four-sided figure. That's all you can determine. There's nothing else there to indicate that it's anything more specific than just a four-sided figure. Because nothing's complete. We don't have both diagonals bisected. We don't have both pairs of opposite sides equal. We don't have any angle markers. There's no. Do you see what I'm saying? It's got to match a property before you can conclude it's something other than just a four-sided figure. You can't. There's nothing there. Okay, so that's what you're up against. Section 7.5, there are these problems to do. 3 through 29 odd, and 30 to 34. And I don't know how many that is. 3 through 29 odd, and 30 to 34. I'll tell you how
I feel like
many.
19.
3 through 29 odd, and 30 to 34. Is it 19 you said?
You told us like
Oh, well, I tried to figure it out here. I'm gonna actually count. Yep, I was right. It's 19. So you can miss one is all. It's a bummer. Okay, there you go. Good luck.